Calculus, we're in 6.9, you have a notes page for this. Basically, there's either 3 or 6 things in this that you want to go on your card, and then we'll want to use in the homework. So, it's the derivatives of inverse trig, which is different than the derivatives of trig things. We did before derivative of sine, derivative of cosine. What we're doing now is derivative of inverse sine and inverse cosine, which are the opposites of the trig things we did. Like a trig function, you put in an angle, it gives you a decimal or a fraction. Like sine of 30 gives you a half. Or if you're using your calculator, sine of 30 gives you a 0.5. Inverse trig reverses that. So if you do inverse trig of 0.5, it gives you the 30. Or inverse sine of a half, back to 30. Or radians, pi over 6, you know, those things too. But we're doing derivatives of those things today. That's why yesterday they were brushing you up on the trig review. So I didn't write those 6 patterns on the board, but really there's only 3 patterns. You might notice that sine, if you compare it to cosine, it's the same pattern. There's just a negative on anything with a co. So tan versus cotan, it's the same pattern, just cotan has a negative sign in front. And secant to make cosecant, it's the same pattern, but there's a negative in front. So some people on their note cards, when they prep on, they put 6 on there. That's fine. If you feel comfortable saving some space and just doing 3 of them and remembering the co's are negative, that's fine too. But we're just trying to follow some of these 3 or 6 rules depending on how you look at it. So if we're trying to do the derivative of inverse sine of x squared, I'm looking at the first rule. All of these answers are going to be fractions. It's just a question of how they're going to get created. So sine's pattern is like all of the patterns. Then on top, you do the derivative of the u, which is the thing that you're given here, the argument after the trig word. So for this one, if we do the derivative of x squared, the top is 2x. I'll skip down to this one because every problem, every pattern follows the same pattern. Whatever they give you, do the derivative. Derivative of this is -3. That just goes to the top. The derivative of the u, the thing that's in parentheses or right after the trig word. To do the derivative of this, we have to reimagine this as being to the half power and follow the chain rule that it's half, the parentheses, to the negative half. But every problem, every rule, that's how the tops get produced. There's an item here called the argument, and we're doing the derivative of that. The pattern, it's calling it u for now, but the derivatives of those go on top. What's different, problem by problem, is how the bottoms are going to go. So for sine, the first rule on this paper shows you on the bottom it's the root of 1 minus u squared. Every sine problem would have a root with 1 minus, and you look back to this thing that we're calling u, and we just square that. So if we think about x squared squared, powers to powers, we multiply the powers, and we would get that. That's how the sine problems would go. For tan, I follow the second rule on the paper at the top. We already have the bottom handled, or the top handled. The bottom will go always for tans, 1 plus, and then you look to whatever this was and you square it. If we take this root and we square it, squaring just erases the root. So the root squared just leaves us our regular old x plus 1. This is a little messy looking, so we are going to clean that one up. So let's clean that one up before I move on to the next one. For this, I clean up the bottom. The ones are like terms, so I have an x plus 2. There are invisible parentheses here that I just made visible. Instead of having a half on top, I would leave the 1 on top and put a 2 on the bottom. That's a better way to write the half instead of having fractions inside of other fractions. And I'm going to guess the book most likely would rather have this negative powered thing go to the bottom, because negative powers flip. So I would think likely this would go to the bottom. And if it's to the half power still, it's also still rooted. There is a root still present there. I'm going to guess that's probably how they prefer to do that answer. Third pattern is to do something with secant. So if it's secant, on the bottom we want to do this thing in bars. Always on the bottom of secant, whatever is here would go in bars. And then there's a root. Unlike this root that had 1 minus stuff, we're going to go stuff minus 1. And what we need to do for that stuff is have the u get squared, have this thing get squared. So a negative times a negative is positive. 3 times 3 is 9. X times x would be an x squared. And that's pretty good, but I'm going to still look to clean this up. One way these will clean up is with the bars. If you're doing the absolute value of a negative number, we can pull out instead a positive number. The absolute value of negative 3 is a regular old 3. X is uncertain. X could be positive, X could be negative. We don't know anything about X, so we're going to leave the X, any variable stuff, in bars. These can cancel, and my best answer is a negative 1 on top, an X in bars, and a 9x squared minus 1 still hanging there. And that's like the basic idea, and then I'll show you a few twists and turns that could happen. But that's sort of the basics. Here's a what if, a simple what if. If this were x squared, the purpose of the bars is to make sure we're positive. You're sure that squares are always positive anyway. So if this were an x squared already, you could drop the bars. That's considered simpler. We would want to do that. If I went back to make this secant problem a cosecant problem instead, we would have done the exact same work, but with a sign change. Likewise, if I made this a cotangent problem, we would do the exact same work, but with a sign change. And likewise, if this were a cosine problem, exact same work, but a sign change. So that's going to happen in some of the homeworks. That's why I'm saying you don't really need all 6 patterns written down. You could probably get away with 3 and just do sign changes. The second thing that I would guess they probably do, either now or later with these, is throw in something like an x cubed before it. And now you have to do the product rule. You have to take the first x cubed times the derivative of the second, which we made. So we have x cubed trying to multiply this plus, copy the second, times the derivative of the first. So they might take this same basic element but put it into a product rule kind of question. They might take something and might they do a quotient rule? Quotient rules would seem mean to me because it's already a fraction. And then to put that inside a quotient rule to do another fraction seems unlikely. I'm going to scroll and peek at my book. I will stroll back. I'm looking presently for 14. We'd be working the first 22 of these. And there are not quotient rules. I am correct. Quotient rule, they're not doing that because that would be really pretty mean because quotient rule would have a fraction and introduce a whole other fraction in there. So they spared you the cruelty for once. So we owe them a thank you, I guess. Miss Finney and Thomas did us a favor today. Chain rule. I also don't see any chain rules. But that would have actually not been that bad. Like if they said it was this to the 10th, and they want the derivative. What we would have to do is 10 of those to the 9th, and multiply the derivative of this, which we already had. So that wouldn't be cruel, but I don't see that. Maybe I do. Maybe I do see that once-ish. So that may be around. Chain rule slightly. Product rule I definitely do see. When I do a skim of this, I can see on something like 17, No, 17's doing the product rule, but not with the new stuff. It's like just with old stuff. 21 has a product rule using the new stuff because the X is in front of the inverse sign. And 22 has a product rule because the X in front of the inverse tan. But there's not a lot of the old rules. They're basically just trying to emphasize these new patterns where you go derivative on the top every time, and the bottom you have to follow the pattern established on the notes page. So tomorrow we'll be doing integrals of these, which means we'll have to turn this answer back into the problem we came from. So today we're working forward, and that's going to be, I think, easier. Tomorrow we'll work backward, and that's going to take a little bit more skill to take this and reverse it back. But if you thoroughly understand today's going forward, it will help you when we reverse. We're only ever here for one day because there's only one group of homework. We do 1 to 22 all, that's all we got. So if you have questions, contact me and we'll work it out. See you later.